Uh, he is the smart grid business development leader for GE Grid Solution business and has 48 years of experience in electric utility transmission and distribution industry. He received his BS and MS in power engineering from Purdue, and he has an MBA in finance from the University of California at Berkeley. John is a fellow of IEEE. He's been a member of IEEE for 51 years and counting. So he was awarded the IEEE Millennium Medal, the IEEE Power and Energy Society BS Excellence in Power and Distribution Award, and the PS Substations Committee Distinguished Service Award. Also, he received the IEEE PS Meritorious Service Award and the 2016 SIGRE Distinguished Member Award and the 2016 SIGRE USMC Atwood Associate Award, the 2021 SIGRE Honorary Member Award, and the Smart Energy Consumer Collaborative Lifetime Achievement Award. John is past president of the IEEE Power and Energy Society, the vice president for technical activities, IEEE Division 7, Division 7, past the director of the Division 7, and also a member of the National Academy. John was on the board of governors of the IEEE Standards Association and the IEEE Foundation Director, and the foundation board, the founding board member and treasurer of the SECC. John received the 2009 Purdue University Outstanding Electrical and Computer Engineering Award and will receive the 2023 Purdue University Distinguished Engineering Alumni Award. He must be paying a lot of money for them. He said no, by the way, but yeah, so, was all please help me welcome John to this presentation.
So what I'd like to talk about is not so much what we're doing, what we've been doing, or what we're doing today, but more of the future. Okay. Always, always in addition to work, even though we all spend a lot of time with studies and work, I always say that we need to have a good balance. It's not working.
Give me. Let me try something.
There we go. I needed to put the cursor back up. Okay. One thing we need to have a good balance is between our own health and our studies. Okay. And so I have 4.5 million miles on Delta Airlines for many years, traveling all over internationally. Reached my all-time peak weight 12 years ago at 59 years old. I started working out with a professional trainer, running 5K races and boot camps. So the lower right here, Dez was a Georgia Tech wide receiver and then played for the Chicago Bears and the Atlanta Falcons, 28 years younger than me, but I try to beat him in everything that we do. And the top picture is my son, who is a Georgia Tech double-E in power, 5 years at GE, left 2-year full-time MBA at Duke in energy finance. In the morning after his graduation with his MBA, we ran a 5K race on the Duke campus. Okay. And as I said, I always told my son, someday the old man's going to pass you at the finish line. Of course, he says that'll never happen. So we want to keep, I find that if I stay in good shape, I'll be 71 in December. If I stay in good shape, my work is better because my mind is clear and I'm energized from the boot camp in the morning. And usually I've done something at boot camp I didn't think I could do, whether it's weights or how I did on the rowing machine or the treadmill or the air bike or whatever. So that's important. Okay. Put the cursor there again. It seems to there. these are the things I want to touch on. And I won't, for time, I'd like to cover a lot of these topics. Don't have time to go into a lot of detail, but I'll touch on them. But when we have, if you have questions, we can go into more detail with questions afterwards. Okay. Okay. First thing is, whether you're a student or whether you're working full time and you graduated, I always say that we need to have a balance between internal focus and external focus. In other words, you need to get involved in organizations like IEEE. You need to, like I did, I participated in writing standards about substations and substation automation back in 1987. Next year, I volunteered to be a working group chair, then a subcommittee chair, and I was chair of the substations committee. Because if you don't get involved in outside activities like IEEE, these key industry trends, you won't be familiar with those. If you're 100% internally focused, you may do a good job with your work or your studies, but what's going to happen is the risk is you're making decisions that you think are optimum, but they aren't, because you don't know what's happening in the world around you. You could recommend to your company to buy equipment from a vendor. A new industry standard is published 9 months later for the new communications protocol. And now all the vendors have adopted that protocol, except the one you bought the equipment from, because they weren't involved in writing the standard. And now the equipment you convinced your company to buy is obsolete. Okay? And you're responsible for that, because you didn't know what's happening in the world around you. Okay? So some of these trends are, back 1984, we saw the first microprocessor-based relay. And this was revolutionary to us because it had two-way communications capability. Remember, the previous devices, electromechanical, were standalone, single function, no communications. Okay. Now, we could put these devices, they could be a node in a bigger network. And so we teach students now, always think of the big picture. The big picture, the holistic solution, we'll talk about that in a minute, has much greater benefit to the customer than the component itself. And use the two-way communications, integrate that component and relay, monitoring diagnostic device. And I'll show you in a minute here 6 examples of 6 solutions. Okay. Holistic means enterprise-wide. You don't want to just provide a solution to one group in the utility, but you want to break the silos down among the groups and think company-wide. And a solution is a set of technology components integrated together that successfully interoperate, okay, to meet the business needs of the customer. I'll show you 6 examples. Success is like a 3-legged stool. If one leg is weak or missing and you try to sit down, you'll fall over, right? You won't be successful. So these 3 legs are important. Technology, and typically we stop there because we love technology, but that's not enough. Technology today has to be standards-based for successful integration and interoperability. The solutions that we put together the components aren't all from the same vendor. They're from different vendors, okay? And one of the most challenging projects you could have when you graduate and you work for a company is your manager says, here's components from 6 different vendors or 4 different vendors. I want you to connect them together, have them talk to each other successfully, exchange information, and implement that in the field. And even though all those vendors say we've all incorporated the communications protocol, typically here in North America it's DNP3, Distributed Network Protocol 3, we've all incorporated that. There are some incompatibilities in those implementations that cause initially those components not to successfully communicate with each other. Okay, so standards are important, and then policy. Policy is the strongest driver to incentivize the customer to buy our technology. Okay, in the state of Georgia, I live in Atlanta. We had a $7,500 tax incentive for people to buy EVs, buy or lease EVs. When we had that, Nissan couldn't keep Nissan Leafs on the lot. Everyone wanted a Leaf. When that expired, almost 2 years ago, there was no interest, not the level of interest, because that tax incentive was really driving people to do it, okay? Policy is extremely important. So we spent a lot of time with policy makers. Grid flexibility and self-healing is important. I'll talk more about that. You know, I have logic I could put on the distribution part of the grid that automatically detect the fault, locate the fault, isolate the fault, and restore service upstream and downstream of the faulted segment within a minute or two with no human involved. It's truly self-healing. The focus today is much more on resiliency of the grid than it was before. And with resiliency, there's much more focus today on microgrids. Okay? Many utilities are putting in microgrids to help with the resiliency of the grid. Previously, a microgrid had 3 niche applications: military bases, university campuses, and rural villages. Okay, and our first microgrid project in 2010 at GE was a rural village in British Columbia called Bella Coola. I'll show you that system diagram in a minute. So today, like Commonwealth Edison in Chicago is putting in 5 microgrids. You might have read about the Bronzeville Community Microgrid is very strategic, and it's for resiliency. Okay. Next week we'll be in Chicago for the CGRAE U.S. National Committee Grid of the Future Symposium. I have 116 papers being presented next Tuesday and Wednesday in 29 paper sessions. And Commonwealth Edison is a host utility. I have about 18 papers just from Commonwealth Edison on the things that they're doing, and a lot on these. And we have a technical tour of this microgrid on Thursday next week. I'll talk more about big data, the cloud, use of social media. I wrote the first chapter in a book published about 4 years ago called Big Data Application in Power Systems. So I've been involved with 5 books. That's the most recent book that I've done. And the first chapter I wrote is called A Holistic Approach to Becoming a Data-Driven Utility, right? And I'm going to talk about why organizations today want to have a digital grid. You know, digitization is what's important today. And that involves data, analytics, user experience, and what we call observability strategy. There's a real focus on data today. You know, observability is important. Observability means if you're an electric utility and in a control room, is your service territory 100% observable? Do you know what's happening in every substation, every feeder, every transmission line? We have 52,000 distribution substations in the U.S. Only 2/3 of those today are observable at the control center. So 1/3 of our distribution substations have no automation equipment installed today, because we haven't really invested in distribution historically the same way we've invested in generation and transmission. So there's a big focus. And then the other thing is convergence of operations and IT. 2 groups in a utility that really don't see eye to eye, and they don't really get along with each other. The problem is we have a lot of valuable data on the operations side that we need to get out across the firewalls over the corporate network so it can be shared by other groups in the utility. And by other groups, I mean 25 to 30 other groups. Okay. So this is what I mean about converging these 2 groups. Historically, they don't work well together. And I've had to do projects where I built a enterprise data mart on the operations side of the utility because we couldn't get IT support. Okay, so this is very important, bringing together the electrical and information infrastructures within the utility. Okay, and then the color kind of washed out here, but you know, my work has been adding intelligence to grid for over 48 years, full time, 6 different companies. And what I wanted to show on this slide, can you see it here? Okay. The old grid should be light gray, and that should be halfway here and to the left, halfway here and to the left, and all of this. And the new stuff should be green, which is halfway here to the right and halfway here to the right. And what I wanted to show was, you know, the concept or the term smart grid, those of us that have been around for a long time, we said, wait a minute, this isn't new. I've been adding intelligence to grid for almost 50 years. I'd rather say a smarter grid. What we're doing, in 2007, we had called the Energy Independence and Security Act in Washington, D.C., and Title 13 of that legislation defined what the U.S. should be doing with smart grid. And that kind of coined the term smart grid. So that was, what, 15 years ago. So I would say the last 10, 15 years, it's light green is what we're doing. So voltage control, for instance, we've been doing for a long time because voltage is directly proportional to load. So if you're a summer peaking utility, like many are, and you're contracted to buy electricity, if you exceed your previous peak, there's a severe financial penalty. We would put logic in your system so that if you approached your previous peak in a hot summer day, if you lower the secondary voltage, you lower the load. Okay, and we would do power factor control separate. You know, switching capacitor banks on distribution feeders to reduce the losses. What we're doing today on a distribution management system, or we call advanced distribution management system, ADMS, is we've integrated voltage control and bar control as one application. It's called integrated volt bar control. And that's the light green part. That's what's new. Okay. We have specialized sensors that we're adding to the grid, things that we didn't have before. There's a new family of sensors called monitoring and diagnostic, M&D. Okay. And if I take the oil from the main tank of the transformer, I can bring it through that sensor and I can detect up to 9 different gases dissolved in that oil. That's very important today because we don't want to be reactive anymore. Reactive was where we waited till a transformer exploded and destroyed the whole substation. Then we reacted. Uh-oh, we need to do something. Wait a minute here. Why can't I detect that problem? And before I have the catastrophic failure, let me address the problem, whatever the problem is when it begins, and prevent the big failure. You know, that's being proactive. And that I'm going to show you, that's what we're doing today. What health information do I need from the asset? What analytics do I need to analyze that health information? I want to predict as many failure modes of the asset as I can and prevent the big failures from happening. That's called M&D equipment, monitoring diagnostic, focused on data, focused on analytics, okay? And so these sensors, if I see one of these 9 gases being generated in the oil of the transformer, that's a specific failure mode that I know is occurring in that transformer. And the rate that that gas is being generated tells me how quickly that transformer is degrading. That gas is being generated a lot quickly, I better get right onto it. Okay. So this is what we mean is when a utility says, you know, do I have data coming back from parts of my service? Is it observable? Second, am I getting all the data that I need? Because remember, and this happens a lot, we love these new analytics, these applications. We buy one, we install it, and we only feed it the data that we have currently coming back from the field, nothing new. And all of a sudden we say, how come that application isn't giving me all the results that I expect? Because I'm not giving it all the data that it needs, okay? We need to focus on data. An analytic, an application can only optimize what it knows is happening. If you limit the data that you're giving to an application, not giving it all the data it needs, you're limiting the value that it can provide you, right? So you got to focus on observability, on data, okay? Okay, so think about, you know, what would an electric utility want to implement to give it the greatest value? And these are 6 holistic solutions that have tremendous value to electric utilities. First is asset optimization. Okay, we talked about that. We started with transformers. That's a multi-million-dollar asset. Okay, the average age of a transformer in the U.S. is over 42 years old. All right, so we want to make sure get the health information from a transformer, analyze it, and prevent a failure from happening. Second, now we've moved to high voltage and medium voltage circuit breakers. So we have monitoring and diagnostic equipment for transformers and for circuit breakers. So we're getting health information, and we're looking for, we know the failure modes, and we're looking for those, and we're preventing a catastrophic failure, okay? That's probably the second strongest business case of these six, all right? Second is demand optimization. We're aggregating load, demand, and today in an EMS, in generation transmission control center, we're using aggregated load as a dispatch tool. We're not doing traditional automatic generation control anymore, where we ramp units up and down. But it may be more economic, instead of moving a unit into a less efficient operating zone, we can pull the trigger on some load for a lot less money, right? And I can cycle the air conditioner in your home. I can turn it off for 7.5 minutes every 30 minutes and save a tremendous amount of load. And the temperature gradient in your house doesn't change. You don't know, you don't even feel it. Okay. If I have thousands of homes, I turn off their central air 7.5 minutes, and then I rotate that. I have thousands of homes in one block, another block, another block. I could save a tremendous amount on a peak day. Okay, but the homeowners don't even know it's happening. And I can use that as a dispatch tool in the control center. Third is smart meters, two-way communications. Talk more about that. The strongest business case of these six today is distribution optimization. For many years, there was very little investment in distribution, very low power factors, on feeders, a lot of losses, okay? And it prevents us, when we want to integrate renewable energy, distributed generation on distribution, this prevents us, the losses prevent us from doing this because we have no hosting capacity. You might have seen that. Hosting capacity is the ability to integrate distributed generation on the distribution. Why? Because it's being taken up by losses, okay? So if we focus on, and I'll show you some low voltage power electronic controllers that we use on the distribution grid, reduce the losses, frees up hosting capacity. Like Hawaii has targeted, the islands of Hawaii have targets of 40% of their generation must be renewable in a few years, okay? They had so many losses on these islanded power systems until we installed this low voltage power electronics, and through continuous set point control, we reduced the losses, and it freed up a tremendous amount of hosting capacity, and we can now integrate a lot of distributed generation on our grid. So we'll talk more about distribution. The benefit cost ratio today, for every dollar I invest in the distribution grid, I get $5 to $6 back. So the benefit cost ratio is very, very attractive, 5 to 6 to 1. Payback periods are usually 3 years or less. Transmission optimization, the focus today is more on synchrophasers. There's a big difference. Typically, the data we use is 2 to 4 to 6 second data. We call it SCADA data, Supervisory Control Data Acquisition System. The SCADA data, the data that's sampled at the rate of the master station and the control center. But with phaser measurement units, we're getting maybe 50 samples per second. And that gives us a lot more granularity, gives us a lot more insight into the grid. So at first, we brought that information into the state estimator on the energy management system. Now we're doing wide area measurement systems, right? That's what I call it. And then lastly is workforce and engineering design optimization. We say we have an aging infrastructure, but we also have an aging workforce, right? When I took over as IEEE as president in 2006, the average age of our member was over 50, and the average age of the IEEE member was 42. So we needed to figure out how we could attract students and young professionals. In 2008, we changed the name of the society from Power Engineering Society to Power and Energy. Why? Because we found that young people really wanted a healthy environment, help society with the work that they did. And so we've, since we changed the name in 2008, we really emphasized the energy part, renewable energy, helping the environment, helping society. And that's why we're the second largest society now in all of IEEE of 39 societies. We used to be the third largest, and now the second, a little over 40,000 members. Okay. Now, with workforce, though, in the next 5 years, 40 in the U.S., 40% of the employees in the energy industry and 60% of the executives will retire. The challenge is that all the experience that these people have will go. Okay? When you're at the university, you learn the science of engineering, textbooks, professors, courses, but anybody can learn that. That's not the value you would bring to a company when you work full time. The value you bring to a company is the art of engineering. And that's how do you apply the science in the real world. That's the value you bring to a company and the company's customer. And you can't learn that quickly. You have to spend years with experienced people, work side by side with them. So that's why when these people retire, they take all that with them. Okay? So that's why mentoring, I can't emphasize enough how important mentoring is. Every student, every young professional should have at least one mentor and spend as much time with that mentor as you can. We just started a mentoring program in the IEEE Power and Energy Society. We just started one in IEEE Eta Kappa Nu, which is the Electrical Engineering Honor Society. Okay? Because mentoring is so important. How do you accelerate your understanding of the art of engineering as a young person? With a mentor. And spend as much time as you can with that mentor. Ask questions and learn from them. Okay? The value, and that would come through in any interviews you have, in any interaction with the company, because they would right away see you have more of a depth of knowledge and more of a breadth of knowledge from your mentor than other people your age. Okay? So that's workforce is very important. And you really need to know the art of engineering. Okay? This is the technology roadmap for those 6 solutions. This is what I mean success. Think of, let's look at the light blue boxes. That's just the distribution optimization holistic solution. Upper left is control center or office, lower left is substations. This is the distribution feeders. You've got, those blue boxes are from different vendors and they're all over the enterprise. They have to be able to talk to each other and exchange information successfully. This is what I mean. This is your big picture. Okay, think of the big picture. Don't just think about a capacitor bank or a switch, right? Or the distribution management system. These are 4 software applications on the DMS. Don't just think of one component, but think of all those components working together. The holistic solution has much more value to the customer than any of those components. Okay, and that's what you want to bring to the customer. But you have to understand all these components and how they work together. When we put those 6 solutions together, you can imagine all the permutations and combinations we had for all the components that we have. How do you put them together in a way, though, that brings a lot of value, the most value to the customer? Okay? And integration is extremely important. The 2 key words, integration and interoperability. So the 5 key components that are important today are smart meters, and then AMI is the smart meter communications, 2-way communications, called automated metering infrastructure. The geographic information system, the outage management system, and the distribution management system. But it's the integration of those 5 together and the integration of those with other systems in the enterprise that is a measure of how resilient the utilities grid is. For instance, with a smart meter, not only do we get the meter readings, but we ping certain meters at the ends of certain feeders to get the voltage. Because when we do integrated volt-var control, we flatten the voltage profile, and then we lower it. We have to make sure on a long feeder with a lot of voltage drop that the very last customer, we have a standard in the United States. All countries have a standard. Ours is ANSI C84.1, American National Standards Institute. The voltage at your home must be 120 plus or minus 5%. The 120 minus 5% is 114 volts. I got to make sure when I do integrated volt-var control, the voltage at that very last customer is above 114 volts. Typically, we set that at 116 to give us some buffer. So we can ping certain meters to find the voltage. Okay, so there's a lot of integration here to be successful. The geographic information system is the reference system for the network model, the outage management system, and the distribution management system. Okay, so we can integrate distributed generation at the transmission level, the distribution level, and the end user level. We'll look at distribution and the end user level. What's the challenge today with integrating with distribution? We designed the distribution part of the grid to take advantage of electricity flowing in one direction only, from source to load. It wasn't long ago when if you worked for a utility, you were going to do field work on a distribution feeder. You go out in the field and you say, all I have to do is open the upstream device and I have a safe working situation, de-energized. It's not true anymore, right? I'm integrating distributed generation all throughout the distribution system. I have electricity now flowing in two directions, okay? And that, we didn't design the distribution grid for that. So it's the unique challenges in the grid, two-way power flow, and I'll show you problems with voltage or challenges with voltage regulation. What are some of the challenges? Protection ratings today don't match fault currents. Okay, when I was going to set the protective relays, first thing I do is do a short circuit study. When I do the short circuit study, I typically only look at the source side contribution to the fault. I didn't consider the load side, right? Because for years we didn't have a distribution, a significant load side. Now, when you have a high penetration of distributed generation, you could have a significant load side contribution to the fault. We didn't take that into account with our short circuit study. So our protection ratings don't match our fault currents. But the other thing is the fault currents vary with the distributed generation. Is the sun always shining on the PV panels? No. What if a fault occurs on a very cloudy day? There'd be no load side contribution of fault. What fault occurs when the sun's brightly shining and all those PV panels are generating? Could be a significant load side contribution of fault. How do you set the relays then? Right? Depends when the fault occurs. So varying fault currents due to the intermittency of the distributed generation. All right. This is the first microgrid project we did 12 years ago at a rural village in British Columbia called Bella Coola. And you can see that, well, this rural village, meaning this village is not near any electric utility. Okay. They have their own hydrogen fuel cells, PV panels, low head hydro generation. But typically, the base generation is diesel. Well, we wanted to minimize the diesel generation. It pollutes the atmosphere. Plus, transporting diesel fuel to a rural village is very expensive, and maximize the other resources. So we took a microprocessor-based relay in the upper left, and we added logic to it to become the microgrid controller. And we added these blue boxes here are high-speed communications boxes. And there's industrial and residential load that we need to satisfy all the time, okay? So every 2 seconds, we're optimizing, making sure the load is satisfied, optimizing the use of the resources and minimizing the use of the diesel, okay? And you can find papers on this online, Bella Coola. And again, it's been operating for about 12 years now, okay? This is a couple of microgrids at the old Philadelphia Navy shipyard, where Navy ships were repaired or built. And that's now an economic development zone. And this was started by Alstom Grid prior to 2016 when GE and Alstom Grid came together. And this is quite a complex here that you can tour. We have several microgrids. Each one has its automation control system. We have a control center with a DMS, distribution SCADA system. And also they use, you're probably familiar with Grid Lab D is open source software written by Pacific Northwest National Lab. It's free, it's open source, and you can model the grid on a full 3-phase unbalanced basis using that software. And that's what they use for modeling and analysis. Okay. How do we handle the intermittency though? When you turn your lights on at home, if it's a cloudy day and the sun's not shining, you still want your lights to come on. So what provides the electricity? It's not the PV panels. So how do we deal with the intermittency? Well, obviously one is energy storage. Another one is a new family of turbine generators. They're very fast starting, fast responding, and they use natural gas as a fuel. So there's a lot of new technology today to handle the intermittency. A couple of years ago, you might have seen GE announce a new electronic gas hybrid turbine, which is an integrated package of 10 megawatts of lithium-ion batteries and 50 megawatt turbine, fast start, fast responding turbine generator integrated together with software that optimizes the integrated operation. Southern California Edison was put in a couple of these right away. So that's what we're seeing, you know, the penetration of distributed generation is growing, but how do we handle the intermittency? How do we deal with the intermittency of that? Okay. And this is, I want to talk about the convergence today of power electronics with power systems. And I've got in a couple slides I want to talk about that. I've been preaching for almost 15 years now. I was president of Power and Energy Society and worked very closely with the president of Power Electronics Society at the time, Deepak Diman, professor at Georgia Tech in Atlanta. We spent a lot of time in his lab. We can't silo these society. You know, we need everything in the world today is interdisciplinary, right? I learned a long time ago, if I wanted to be a power system engineer and focus on automation, I needed to learn a lot about communications, right? Any automation system has three components: master station, field equipment, communications, that ties it all together. Okay, you can't just focus on the power system applications and that kind of stuff. You got to know a lot about communications. Okay, and everything's interdisciplinary. So this is low voltage power electronics, and I wrote this article over 9 years ago in Power Electronics magazine. I was working with San Diego Gas and Electric, and they had a situation that happened on their distribution grid that they had never experienced before. And they came to us at GE and said, "Oh, you know, look at these voltage waveforms we have on the distribution feeder." So what happened was, if you consumed electricity in California, you paid 10 cents a kilowatt hour. The policy changed. If you could generate electricity, any excess that you would sell back to the utility, they were required to pay you 40 cents a kilowatt hour. That spread, the greater the spread, the more attractive the business case, right? So one feeder, San Diego Gas and Electric, fed very expensive homes along the Pacific Ocean. So these are homeowners that had money that could buy PV panels and put them on their roof. On this one feeder, over 35% of the homes installed rooftop solar panels. That's it's pretty high penetration. Okay, so the tap changer in the substation is supposed to keep the secondary voltage constant, no matter how the primary voltage fluctuates. Right? You want your light bulbs in your house to be the same brightness, no matter how the voltage fluctuates. If there's no tap changer, you would have very bright, very dim, very bright. Your bulbs would. So the tap changer is a mechanical controller with 16 raised positions, 16 lower positions, and a neutral position. Each change is 5/8 of a percent of volts. And the more volatile the primary voltage is, the more times it operates. On this feeder, it was operating about 5 to 10 times per day, okay, with a lifetime of 35 years before it had to be replaced. Remember now, it's a mechanical controller. The more it operates, the less its lifetime, right? So all of a sudden, over 35% of the homes install rooftop solar panels, okay? There's a marine layer of fog over these homes in the morning from the Pacific Ocean. As this fog burns off, all these homes begin generating, okay? And San Diego Gas and Electric sent us the waveforms. At the beginning of my article here, you can find this if you search the internet, Power Electronics, and my name, find it. I have the voltage waveforms at the beginning of my article. You wouldn't believe it. The voltage would spike, okay, and then oscillate as the clouds went in between the PV panels, right, in the sun. This tap changer now is operating over 150 times per day. Its lifetime was now less than 2 years for it had to be replaced. So what we're saying is, in this article, a couple things. One is, there's new applications of power electronics. I really want power electronic grad students or researchers to work more closely with power system folks, because 3 applications I happen to talk about in the article: online tap changers, new family of devices, low voltage network dynamic grid edge controllers. We're installing these low voltage power electronic subpoint controllers on the low voltage network where we have a high penetration of rooftop solar PV. Okay, and then smart inverters, more functionality from the inverters and more external control capability. Remember, an inverter is a good VAR source, and the higher the penetration of distributed generation, we can use the inverters for VAR support on the distribution system, and we don't have to install as many cap banks. Okay, and we've done a lot of studies, the trade-off between needing cap banks and as the penetration increases of distributed generation. Okay, so this is the future grid is much more volatile as the penetration of distributed generation grows. Mechanical controllers just aren't feasible anymore. Okay, and we've learned a lot with experience so far with respect to forecasting and the thermal fleet, which is much more responsive, the generation, and faster starting. But we also still have a lot of challenges. Like we have a lot of unobservable distributed generators that are out there connected to a utilities grid with very little, if any, information coming to the utility. Okay. The other thing is, we found that there's tremendous impacts that you don't even think about when you start implementing large amounts of distributed generation on your grid. And these are just examples of some studies that we've done at our energy consulting group at GE with wind. Okay, you really have to model it, study it, and really do a deep dive into what the impact is going to be. So one thing, because the distribution system is more complex with two-way electricity flow, possible congestion, things that we never experienced before, utilities say, I need a separate SCADA system for distribution to manage the complexity, which you hear ADMS, Advanced Distribution Management System. And there's 2 parts: the basic SCADA platform, supervisory control, remote control, and data acquisition, and then the applications on an ADMS that optimize different parts of the distribution grid. Myself and Dr. Jiwan Fan, for years now, we teach a full-day tutorial just on this subject at an IEEEPS meeting. We taught this tutorial in New Orleans in April at the T&D conference. This also was recorded by IEEEPS. The 5 PowerPoint modules we use are online. They're available online. So there's a full-day tutorial on this subject. But we get all the information from the field, we analyze that, optimize the distribution grid, and then send control commands back to the field for optimization. Okay, and then the reference system we said is the geographic information system for the network model. These are the applications we typically find on the ADMS that the operators use in real time. Okay, and in our tutorial we go over each of these in detail. This is the group of applications used for analysis. Okay, and then this is the group we call ancillary group that many utilities say, I want these applications to be on the ADMS also. So you can see it's a fairly involved set of applications, right, that provide the utility a lot of value. What's interesting is utilities say, I want a digitized grid. Okay, but realistically, no organization can get there in one step. They don't have enough budget money. They don't have enough people to support that, right? So we said, okay, we'll help you put a roadmap together. What are the steps that you can take? So the first step is, where are you today? And the utility might be manual control and legacy methods, okay? And let's put a roadmap together. What are the steps? Each step has a reasonable amount of budget money, reasonable resources needed, people resources, but also each step should provide significant benefits back to the utility. So here's the first step: remote control and monitoring, trouble calls, smart meters, circuit reclosers, 28% lower customer minutes interrupted than the base level. That's significant. Next step is automation and visualization. Distribution automation, that's 43% lower customer minutes interrupted from the base level. And then digitally enabled and much greater than 50% than the base level. Okay, so you put a roadmap together, reasonable steps, right? And then you can see a long-term plan for the organization. Okay. Another one is utility. Before I joined GE, I did a lot of international consulting for utilities, and they would come to us and say, we're in the third quartile with the reliability of the distribution part of our grid. So that's below the middle point, right? Third quartile is not very good, okay, compared to other utilities, right? First quartile is the best. Second quartile is second best. Third quartile is third best, or second from the lowest, right? So they say, what would it cost us to go from the third quartile to the second quartile? Very, very common question. What would we need to do? So let's take this utility, 856 distribution circuits. Wow, to automate 856 circuits, tremendous amount of money. But do we really need to do that? So we studied this in detail and said, only 23% of all those circuits contribute 71% of all the outage minutes. Okay. So if we automate just 23% of the circuits, we're addressing almost 3/4 of all the outage minutes. Much better use of money and a much bigger return on the money spent. Okay, so I think why I got an MBA after my master's is we need a good engineer. We need to know the business side of the technology. And I see many young engineers with very good ideas for technical projects, but they're frustrated because they can't get their projects approved because they don't know how to express their project in business terms. Okay, the senior executive at the company wants to know, what are the anticipated benefits if I spend this much money? What's the payback period? How many years does it take for the cost curve to cross the benefits curve? Right? So executive may say to you, okay, for every dollar I spend on your project, how many minutes of SAIDI will you save me? In other words, for every dollar I spend on your project, how will you improve the reliability of my grid? Or for every dollar I spend on your project, how many millions of tons of carbon dioxide will you prevent from going to the atmosphere? And what you do is you calculate, okay, by adding automation to the substations, it requires less times for a truck to go to the substation. How much CO2 comes out of the tailpipe of the truck? Okay, what's the average distance? How many millions of tons of carbon dioxide can I save from going into the atmosphere by implementing my project? Okay, you really need to think in terms of all the value streams that come out of your project for the executives. Okay. Now the other thing is, when we look at a microprocessor-based device, we only focused on this data because this is all we were concerned about for many years. The data from the field that goes to the control center that the operators use. And that's all we had available until 1984 when we got our first microprocessor-based device. Now with microprocessor-based devices, in addition to the operational data, which is points of data for the operators in the control center, we have a whole bunch of non-operational data. And there's 25 to 30 groups in the utility that need this data, not just a few. Maintenance, power quality, asset management, planning. And this is both points and files, like a sequence of events report from a relay. When a disturbance occurs, you want to know what happened first, what happened second, do your root cause analysis. Okay, and the sequence of events report will give you that information to the nearest 1 millisecond resolution. Okay. I squared T in the relay gives you the idea of circuit breaker contact aware of the circuit breaker the relay is connected to. Okay, so this is very important information that we don't pay enough attention to. I wrote an article in IEEE Power and Energy magazine in 2003, guest editorial, that introduced these concepts to the industry about 19 years ago. So comparison of operational data and non-operational data. Operational is real time or near real time. And non-operational is mostly historical. Both very important. And then what's really cool is think of the Internet of Things. It's really a huge productivity revolution that we're all taking advantage of because by connect, I mean communications, right? Communications is key here. We're connecting intelligent machines, okay, with big data and analytics, and with people, connecting people any place, any way, anytime for intelligent operation. How do we leverage that to the advantage of our company, who we work for? Okay, tremendous savings here. And what it does is it really puts emphasis on data and analytics. So on the left here is a typical situation in an organization today. Wherever, and I, as a consultant, I saw this all the time. Every individual group in the organization has its own systems, its own devices. The IEEE term for the devices, we introduced this in the 1990s as intelligent electronic device. So if you hear IED, that's another term for microprocessor-based device. There's two parts to the definition, IED, internal processing capability, but the most important one I said earlier was two-way communications capability. Intelligent electronic device. So every group has its own systems, devices, and data repository. And literally, it's very strongly siloed. There's no sharing. So as a consultant, I would find the same piece of data from the same device in the substation in 4 different groups' databases. Each of the 4 went accessed in what was supposed to be a cyber secure system in the substation, and they didn't talk to each other. They didn't share. And this is what I would help the utility do, is break the silos down, have like a federated data mart, and bring all the data sources together and map the available data with all the users, both operational and non-operational users. Make sure that all the users had the data that they needed so they could provide the most value to their organization, okay? And the result is we have standard architectures. This is an architecture in a substation with a master data concentrator, slave data concentrators, talking downstream to a lot of microprocessor-based devices. This is all the data sources in the enterprise. There'd be a bunch of these in cyan or light blue. And in green here is all the users throughout the utility. Operational users, non-operational users, satisfying now their data needs, okay? So they have the data that they need from all the data sources, okay? And this is the coolest part. This is why, you know, people say, John, when are you going to retire? You know, and I said, why would I'm having more fun. Never. I'm having more fun today than I had before. And this is why, you know, we started at reactive, and that's all we did. We waited for something to explode. And then we said, oh, well, what do we need to do now? We got smart. We said, let's be proactive. Moved from responsive, today we're predictive. We're doing a pretty good job of predicting as many of the failure modes of an asset as we can. What health information do we need? What analytics do we need? But what's cool about this is we're only halfway of where we could be. Okay? And what we're doing is, and what we did in this book, Big Data Application of Power Systems, talk about artificial intelligence, machine learning, the digital twin, you know? And with more of that, we can be prescriptive and eventually autonomous, self-healing, self-provisioning, and extensive autonomous operations with limited human intervention, okay? And I can't say enough how important standards are. That's why I got involved with the Substations Committee in 1987 and chaired the whole committee 2001 and 2. You know, there's 39 societies in IEEE. Power and Energy Society is one of 39. Yet the Power and Energy Society writes 50% of all the IEEE standards. Okay, 50%. We have 17 technical committees, completely voluntary. As a student, you can join any of the working groups and any of the technical committees. 17 technical committees, 4 coordinating committees. One of the technical committees is substations committee. Okay, so from 2009 to 2015, I chaired a board for the U.S. government of 25 industry experts. We were in charge of all the smart grid standards work for the U.S., called the Smart Grid Interoperability Panel. And NIST was the government organization that we did this for. This is the Smart Grid Conceptual Reference Model. If I tell you smart grid, the landscape of smart grid is turbine to toaster. You say, wow, that's a big landscape. Power plant to your home. Okay, and I gave you one sheet of paper. I said, I want you to draw that entire landscape on one sheet of paper. Okay, what would you draw? So this is the 7 domains of smart grid and how they interact with each other. And then we did a deep dive into each of the 7 domains. So it's 8 PowerPoint slides. And this is in its 4th revision with NIST. Okay, we just finished the 4th revision just prior to COVID. But the biggest thing we did was, IEEE right away said, well, we have over 100 standards that are involved with smart grid. And IEC said, well, we have over 100 standards. So let's say you're buying a product at a utility, you're writing a spec, or you're developing a product at GE. How do you figure out what standards are relevant to what you're doing? No one's going to go through hundreds of standards. So we said we need to help the industry. And these are the 16 foundational standards for smart grid. Okay, these truly cover, this is all you need to be concerned about. This was our goal. How do we be inclusive of the entire landscape, but have a manageable number of standards? Okay, and these are all the key standards that cover generation, transmission, distribution, your home, cybersecurity, everything, integration of renewables, home automation, right here. So these are the 16 foundational standards for smart grid. Okay, and what's neat here, because I've been involved for a lot of years, is 3 hierarchical levels. Control center to control center, there's one global standard today that's adopted globally. Any SCADA system today, no matter where you are in the world, you'll have at least one ICCP port, Inter-Control Center Communications Protocol. That's the standard today for one utility talking to another utility, or within a utility, if you have an EMS for generation transmission and an ADMS for distribution, within your utility, those 2 systems will talk to each other using ICCP. Okay. Now, from control center to field, there's 2 protocols. In North America, we always have used a lot of DNP3, Distributed Network Protocol 3, which is IEEE Standard 1850. European suppliers, we use IEC 870-5, 101 for serial, and 104 for network. Then when we're in the field, IEC 61850 is really the global standard. But again, in North America, we still use the DNP3. But it's very easy. We've converged on a very small number. Okay? And let me finish. I'll finish with a couple slides. Everyone says, you make assumptions when you sell equipment to customers and they implement it. Have you learned anything? What were your initial assumptions? Have you learned anything? And have you taken what you've learned, come back and change the way you're doing it? And very few companies do that. They just keep selling product and keep implementing. After 18 months of a number of smart grid projects, we stopped and reflected back. I've got a couple slides here on the lessons we learned. Okay. Normally you don't see this stuff because people don't stop and reflect back. They just keep going forward. But we found that, remember, a holistic solution is a number of components that are integrated together. When you take a chain and you pull the chain tight, a chain is only as strong as its weakest link. Right? You can have strong links, but one weak link and the chain will break. Think about the holistic solution. It's only as mature as its least mature component. Okay? And so we found that there was a lot of hype initially versus reality from vendors. in terms of the maturity of all the components and the holistic solution. Okay, so there were many cases we had to field re-engineer or upgrade components, but we expected that. You can test all you want in the factory, but the real test is when you get to the field, install. And you expect, you know, like when I wrote a software application, if it ran perfectly the first time, I was suspect. I said, I'm missing something, right? That doesn't work that way, you know? What did I miss? Because when you implement something in the field, something, you know, you're going to have some problem come up when you expect that. Okay, nothing's perfect the first time. Second is the emphasis on integration, interoperability, and importance of standards. Okay, I can't say enough about that. Technology has to be standards based. Third is testing. You can't do enough testing in the factory. It's easier to fix something in the factory. When you get out of the field, it's much more difficult. All the experts are in the factory, but to get those experts out to the field to help fix things is tough to do. Okay, so, but not only testing, but end-to-end testing. At the time, we had smart meters. We sold the smart meter business in 2016, but we had smart meters and we tested them with our communications card. But now we go out in the field, now the meter has to talk upstream to the head-end system, the network management system. We hadn't tested that in the factory. We had problems in the field, and that was a wake-up call. You need to do end-to-end testing. Not just testing, but end-to-end testing, okay? The other thing is, as a vendor, you want every installation to be a happy customer. So they are a good reference for you, okay? And it's not enough to have the world's best technology. You could have the world's best technology and have a disastrous project, okay? And we thought that we only had to be concerned about the engineering team at the customer, you know, in terms of if any components had to be upgraded or re-engineered. But we could have the best engineering team at the customer, the best technology, and still have a disastrous project. What we found was what's critical is project manager at the customer. I can't say enough about how important it is to have a strong engineering team, but a strong project management team also. And what happened was we found project managers that were given the responsibility for the project, but they weren't given the authority to be successful. There's a difference between your boss could give you the responsibility to do something, but not give you the authority to be successful. Okay, you need both. And a smart grid project involves many different groups in the utility. And so these project managers need multi-discipline authority across all the groups, all the stakeholder groups, and there's a lot of them. Okay, so we said, as a vendor, we need to make sure our customer builds an A team with the best engineers, but also project managers, okay, to be successful. All right, and then lastly, a real revelation was in 2007 with the Energy Independence and Security Act, when we read Title 13 about what the U.S. should be doing with smart grid. We said, whoa, this is new. All of us at that point in the industry, we were experts on the grid, upstream of the meter. Okay, all of a sudden now, we have a new major stakeholder, that's the end-use customer. We've never engaged with the end-use customer. A meter reader would read the meter, take the meter reading back, the utility would generate a bill, customer would write a check, right, pay the bill. There was never any engagement with the customer. The early utilities that installed smart meters with no engagement of customers, tremendous backlash. Right? Customers were saying they didn't understand the new capabilities. They were saying this smart meter has caused my bills to be higher. The smart meter has radio frequency emissions that are causing cancer to my family. Okay, all kinds of stuff. It was lack of awareness of you know, because there was no engagement. So we learned right away. Florida Power Light did a great job when they put in their smart meters. These were GE meters with Silver Springs Communications, 4.5 million meters. but a lot of time was spent with working town hall meetings and working with customers. The end use customer. So in 2010, we formed a new organization called the Smart Grid Consumer Collaborative, which just focuses on the end use customer. You know, there's 5 distinct segments of customers with totally different characteristics and different price points. You can't generate a program for customers and expect all customers to behave the same way. There's actually 5 distinct sets of customers, 5 segments. You have to know what those are. Okay, and then engage. When you engage, you have to know, you know, does this customer want to be green? Does this customer want new technology? Is this customer a traditionalist? So no matter what I tell them, they won't change. You know, there's all these different sets. So that's why I helped found this new group in 2010, and I've been a founding board member of that group for 12 years. Okay, I personally, in the industry, needed to learn more about the value proposition of the end use customer and understand the end use customer. Okay, so I'll finish there. That's a lot of things going on, but a lot of key things. I think a lot of opportunities for you with respect to what we need to do in the future. A lot of different areas that I talked about. All right. Thank you. Questions? Don't be shy.
So let me start. So we didn't talk much about the electric vehicles and the evolution. How is that going to impact the framework that you explained?
Yeah, electric vehicles. You know, it's inevitable, right? And the rate of people buying electric vehicles is very much policy dependent, as I talked about. Okay. Remember that in the U.S., generation and transmission is governed nationally by FERC and NERC. The complicating thing for us with policy is the distribution part of the grid and the end use customer is governed by 51 different public service commissions, 50 states and the District of Columbia. They're all very different from each other. So if you're the CEO of a utility like American Electric Power, it covers 14 states. You can have one strategy for generation and transmission. We have 14 different strategies for distribution and the end use customer. Okay, you know, in terms of rate of return and stuff like that. So electric vehicles, you have to look at the Public Service Commission, you know, rate of return. But the other thing is how do you know, you have to, like I said in San Diego, where, you know, electric vehicles won't be adopted, you know, the same spatially, the same way across your service area. It's going to start with subdivisions that are more affluent, okay, where people have more money. Okay, like in San Diego, these homes put up rooftop solar panels. Why? They were very affluent homes, very expensive homes. So the thing is, you really have to forecast, look, okay, where are my more, you know, higher average salary subdivisions and customers? And there'll be a much more density of electric vehicles in those areas. Then you say, okay, how is my grid, you know, my distribution transformer, capacity of my distribution lines in that area? Okay, and you really have to look at that. So the other thing with electric, and the other thing is, initially we looked at the Department of Energy said, when we overnight, when the loads are a lot lighter, right? And we turn down, scale back a lot of our power plants because the loads are not as great. If we used all that excess generation to charge electric vehicles, the calculation was we could charge 10 million electric vehicles just with the existing generation resources we have overnight. Okay, that's because the load's a lot lighter. So I think, you know, the bottom line is we need intelligence to make sure that we do that properly. And you know, I've like in Georgia Power where I live, we have a special time of use rate for electric vehicle owners because we've had a Tesla my wife and I have a Tesla. We've had a long range Model 3 for over a year. And I have a 50 amp circuit that comes to my garage with a NEMA 50 amp receptacle like you find in a recreational vehicle park to charge an RV. And I can charge it's a 350 mile range car. And I can go from 25% to 90% in about 4 hours. Okay, which is pretty good at 50 amps. But there's a time of use rate for electric vehicle owners saying the electricity is a lot less overnight, right? So, you know, it encourages you, the intelligence doesn't mandate, but it's indirect. It says, charge overnight, the electricity is a lot less. You got to be careful with a lot of these electric utilities because the rate on that time of use rate, the rate during the day is actually higher. So if you're working from home and you're using a lot of loads during the day, my neighbor did that. He bought a Tesla and he went on the time of use rate and his electric bill was actually higher. Okay, so you have to be careful. I think we need to do a lot more with policy. We need to do a lot more with rate structures to make it truly equitable. And I think we need more intelligence into the grid to make sure that charging is truly done overnight, you know, and whether it's intelligence in the car, in the infrastructure, or both. And the other thing is vehicle to grid is another thing that comes up. You know, if the utility needs some generation on a peak day, can they access the batteries in electric vehicles and use that energy vehicle to grid? Okay. Well, on my Tesla, if Georgia Power wants to use some of that energy on an afternoon of a summer day, that's going to increase the charge-discharge cycles of my battery. It's going to decrease the lifetime of the battery. Who's going to compensate me for that?
Are questions allowed?
I was going to say, what happens if I have to go to the doctor unannounced in the afternoon and I don't have enough charge in my battery because the utility's used it? Okay. So there's a lot of issues like that that need to be ironed out.
Is there a question?
Yeah. Go ahead and ask the question.
Yes, I have two questions. Question number one, with regard to the smart grid, what is the status of emplacing the micro generators, the grid itself, including even the micro nuclear generators that may be coming up?
Micro generators.
You know, with smart grid, the real focus is replacing centralized power plants with lots of small generators. They're distributed all across, particularly the distribution part of the grid. And another thing that we're going to see very shortly is commercially available small nuclear generators also. So I would say that it's not, I don't know what you mean by replacing micro generators, because we're really going from centralized power plants to decentralized, distributed, a lot of small generation, but spread out all across the electric grid.
And my second question concerns cybersecurity. What is the status of defense against cyber attacks to the smart grid?
Yeah, that, you know, I would say, you know, I've been working over 48 years, and truthfully, in SCADA and automation until 9/11. Truthfully, we really didn't think about cybersecurity much at all. And after 9/11, it was a real focus on it. What we learned right away was that when you develop new technology, you have to incorporate cybersecurity into the product lifecycle development from the very beginning. Initially, you'd be halfway through a development cycle, and then you try to incorporate cybersecurity, and it doesn't work. So everything that we do today, in fact, I have a PowerPoint slide that's the product development lifecycle that shows how cybersecurity is involved every step of the way. The other thing was I have a separate talk I give on what happened in Ukraine not too many years ago, and how the hackers spent 9 months. It's the anatomy of what happened, and it's like 25 steps where the hackers spent 9 months planning the attack and then launching the attack, and how they got that information. So we, if you look at each of those 25 steps, we've learned a lot in terms of how to have a better defense against that. I know in my company, I think at GE and most companies today, one of the ways those hackers got a lot of information was with phishing emails, right? Where employees would click on a link, or they would open up an attached file, and that would open up. It give a lot of passwords and personal information to the hackers. At GE today, our IT group sends us all the employees phishing emails to try to tempt us, right? To train us how to really look at the emails you get and don't take a chance. If you're suspect, I click a button in the top right of my Outlook that says report phishing email, and it goes to IT.
We have that here too.
You guys do that? I think we learned a lot of that from what happened in Ukraine. Okay, so I think we're much smarter today. We're much, we're taking. One other thing was, as a vendor of SCADA systems, EMS and DMS systems, we typically, all the vendors, we send complete system to the Idaho National Lab. To me, that's the premier U.S. Department of Energy lab for cybersecurity. They have the best training classes, but they also have professionals who they do penetration testing of our systems, and they will help us identify vulnerabilities and help us patch those vulnerabilities. So, before we sell any kind of a new system, Idaho National Lab goes through it in detail with penetration testing, with hackers, hackers and very smart people identify vulnerabilities and help us patch them. So I think, we're doing as much as we can, and we've learned a lot, and as we continue to learn, we continue to do more.
Yeah, one quick question before I forget. You talked a lot about rooftop solar. Okay. Now, in many states around the country, there are a lot of people actually, start to put rooftop. But I'm not sure how does the utility actually, wasn't it agreement, or is it state by state, or is it local, or because I can't directly go sell the power to FGL, say, right? So it's possibly comes back as a negative power. But how this is going to really be sorted out, as more and more people put rooftop.
Yeah. Rooftop solar is really state by state, and really where I live, there's no incentive. Yeah, so you don't see people installing it. In California, it's just the opposite. In Arizona, it's just the opposite. Okay. When I wrote the article 9 years ago, 9 years ago, there was tremendous incentive in California, Arizona, for homeowners to put panels because of the policy. The difference between what it cost you to buy electricity versus what you could sell it for. Okay.
What I meant to this question is how does your equipment handle the more distribution that is going to come with rooftop solar and utility operation? That's essentially going to be a big problem.
Well, the utility in their control center, right, would have to, part of the forecast is given what the weather is going to be. We've gotten better at knowing how much of the day would be sunny and which periods of the day, and forecasting how much local generation there would be. Because the question is, in a control center, if you have a lot of local generation, you don't need your own generation or to buy generation, right? So part of you need to be able to forecast that, right? And so that forecasting is improved. Secondly is, used to be that there wasn't as much information in the early days, people would be throwing this stuff up. There weren't really interconnection agreements in detail. You know, how much information do you need to provide the utility? The second aspect of that is with interconnection agreements. If it was an outside party, not only did you want information, but you want to prevent giving that outside party a cyber backdoor, cyber security backdoor into your network. Okay, so there's much more emphasis today on third parties with cyber, but a lot of it is, you know, high penetration of rooftop solar impacts the control center, and so you have to good forecasting tools, and you have to be able to, you know, manage. That's why we say dispatch is not going to be traditional AGC, automatic generation control, but it's going to be resource optimization. And it's going to be every 2 seconds, I'm going to optimize all the distributed generation that's out there, my traditional generation, and also my aggregated load that I can use as a dispatch tool. So every 2 seconds, every 4 seconds, I'm going to do like a portfolio resource optimization of all these resources to say at this instant time, what's my optimum mix? It's like a portfolio of investments, stocks, bonds, you know, risk return relationships. You want to optimize your portfolio, right, given the current conditions. That's what we're doing. We're going to be doing in the control center.
Okay, so other people with questions?
Yeah, I have a question. So thinking about everything, all of the technological advantages that we have discussed here today, what would you say is the biggest technological advantage that hasn't been done yet that would give the best benefit to our grid?
I would say, I think, you know, what I would, if I was younger, you know, and starting all over again, I would focusing on the power system. I would put a lot of emphasis on data science, because we're just, you know, we're just tapping the benefits of being data driven. Okay, being proactive instead of reactive, being digitized. Okay, I said, you know, the journey, we're like halfway up the curve, maybe even less than halfway. We are hiring data scientists. Utilities are hiring data scientists. Next week, we have a paper competition of just young professionals that are less than 35 years old. 3 years ago, the winner of that paper competition out of 17 young people wasn't a power systems engineer, he was a data scientist. Okay. So what happens when we hire data scientists, they know a lot about data science, but they don't know about the power system. And what's cool is when you start teaching them about the grid, they have suggestions on how we can optimize the grid, but they're untraditional. They're not, our suggestions are from a power systems expert point of view. Theirs are from a data science perspective, which is really cool because it's something, it's a perspective we aren't used to, but it's healthy, it's very healthy. Okay, so I really like working with data scientists, teaching them about the grid, and then just looking at the ways we've done things and how they could be different, better. Okay. So to me, I see so many benefits of combining. You know, if you read the first chapter of the book that I wrote, A Holistic Approach to Becoming a Data-Driven Utility, it shows you how we can combine data science with power systems. And so that's, to me, I think there's tremendous potential there that it's just untapped because we're new at it. It's exciting.
Okay.
So speaking of, I'm currently working on the data science / big data aspect of the smart grid. So I was actually going to ask you a hardcore question because of that exact reason. So I was wondering more about scalability because right now we're at the end of I think our machine learning club with the big data Firebase that we have. So I was wondering what year do you think the smart grids will kind of evolve or become a standard, or what's the most cost efficient way to do it in a sense? That's where we're going.
So if you think of like standards and what we're doing with smart grid, it's a journey. there's really no destination, you know? We learn every step of the way, and then we fine tune future steps based on what we learned. When I was leading the smart grid standards work for the United States, and I had to testify in Washington D.C. before a House subcommittee on C-SPAN, and one of the representatives from Illinois, she said, I have Naperville, a very important municipal in her district. She says, I want to advise them not to buy any equipment until all the smart grid standards are done. When will that be? I said, you know, it's never going to happen. I mean, the standards continue to evolve, and as we learn more things, we have gaps. As technology advances, we have gaps in standards, and that's what we were doing, was identifying those gaps and then writing new standards to handle the new technology. Okay, so what you have to do is be smart about everything that's available today, and be smart about as much as you can what the future is going to hold. And this is why I advocate external focus, being involved in things like IEEE, working groups, writing standards, and things like that, and make the best decision you can. Okay. I always think of a family that's going to buy a new family PC. And they get the Sunday paper and they look at Comp USA and Best Buy. And, oh, you know, there's this great deal, you know, this much memory and hard drive and speed of processor. The next Sunday they get the paper. Oh, there's a new model out that is faster, more memory. And then the next Sunday, the same thing. When do you buy? You can wait forever, right? Because technology keeps improving. See, at some point you say, you know, you make a decision, make the best decision you can based on what you know. So really think of it that way, okay? Think of it that way.
We'll do one last question because we have to eat lunch. Okay? Because he's traveling again now. We'll give him Atlanta going back.
Okay, this is my question. Okay, I have a couple of questions actually. To see the full picture of the smart grid, you will increase observability from generation to the consumer. So this means I know it is better to your eyes to reach it in every point in the power grid, but how you can deal with this big amount of data in the control center, and I think it is better if we make optimal observation for the power grid, like how can select the optimal point from generation to consumers to minimize the scanning the time for every point in the grid.
Yeah. Well, a couple of things. Yeah. One would be when microprocessor-based devices were first available, and I'm working with utilities consultant. Some of the initial engineers would say, John, I spent $5,000 for that device. It has 800 points. I want to get all my money. I want to extract all 800 points from all 20 devices in the substation and set it up the control center. I said, you're crazy. You know, you're crazy. I said, so you have to be smart about data first.
Yes.
And that's why I said what I talked about was look at each device, look at each system. Yeah. What data is available? The device could have 800 points. But what I would go through is every one of those points in the data map of the device. I would say, does this have use anybody in the organization? If it doesn't, I don't extract it. Because nobody's going to use it.
Also,
Okay.
the
I
recording.
developed an enterprise data requirements matrix. And it maps all the data sources with all the users and what data they actually would use. And it's a very small percentage of the data that's available. Okay. So you have to approach these data sources smartly. Say, I'm not going to extract the data point if nobody's going to use it. Okay. You know, that's first. Second thing is that I extract. I don't know if you guys know this, but we've been doing this for decades. We report I report data from the field up to the control center to the substation. You ever heard it's called report by exception? Okay. There's no need to burden the communication system with the status point, like open close of a circuit breaker, if it hasn't changed state between scans. So typically I may have 1,000 points, but every 2 seconds I'm only reporting maybe 50 points, 40 points. I'm only reporting maybe 10% of all the points. Only those that have changed. So we only report a status point every scan cycle, only if it's changed between scans. And we only report an analog point if it exceeds a significant deadband between scans. So when I have a SCADA system, I build the database record for an analog point. I specify a deadband to that point. And if the change between scans is within the deadband, I don't report it. I don't burden the communication system. Now, the challenge with that is when I get into an emergency state, a storm, a lot of wind, lightning, rain, I go from 10% of the points every scan cycle to maybe 50%. A lot more is changing. So for a large SCADA system, I would spend weeks at the vendor's factory testing the system before I would allow it to be shipped to the customer. Because we actually simulate the high activity state in the factory. We simulate 50% of all the points changing every scan. And we look at the CPU utilization of all the servers, we look at the utilization of the local area networks, you know what I mean? So we test that. So, two things to your question. One would be only extract those points that somebody's going to use. The second thing is we only burden the communication system with those points that have changed between scans. Okay, so third one. Only send the operational data to the control center. Additionally, many utilities would take all the data from the field, send it all in the control center, and say, this is going to be my data manager. And what happened was they buy a new SCADA system, and all the memory would be utilized within a couple of years. So take the non-operational data, use the wide area network, and send that over to an enterprise data mart. Only send the operational data, the data the operators need, to the control center. Don't burden the SCADA system with data that the operators don't need.
Thank you, John, very much.
Okay.
We are going to have the slide available on and as well as the recording of this presentation. So thank you all very much for attending, and let's give a round of applause.
Thank you, everybody. Thank you. Hope that was helpful. Yeah,